Okay, what we're going to do now is start with Hermite's idea and extend that to using the same data that was used for the interpolating curve, but use it differently, and we'll get the Bezier curves and surfaces, and the extension of that will be to spline curves and surfaces. And we'll see a progression from having very rough surfaces with a lot of discontinuities in the derivatives that we had for interpolating curves and surfaces up to the smoothness of the Bezier and the much greater smoothness of the spline curves and surfaces. So what we're going to do is wind up with matrices that determine them. So like we had for the interpolating case, we had the interpolating matrix for cubics, and then we got a 4 by 4 interpolating Hermite matrix. With Hermites, we'll get the same kinds of formats for the spline and the Bezier, and we'll also be able to look at blending polynomials and compare them to what we had before to see the extra level of smoothness that we get. So we start with the idea that we don't have derivative data in most graphics and CAD situations. We indicate points either from some model or actually making measurements, but we generally can't measure the derivatives very well. So what Bezier did, and he did this in the 50s, designing car body shapes in France, was to use the same points to get an approximation for the derivatives in the Hermite form. This was in the 1950s, so it was much later than when Hermite did his work for the curves, but as we got into the 50s and started having computers available, then people were much more interested in CAD and using computational methods. So what he suggested was the following. Here's the 4 points that we had from interpolation. Let's assume they're the same values for comparison. So we have 4 points, P0, P1, P2, P3. We want to get a cubic that goes over from P0 to P3 and interpolates these endpoints. But what we'll do with P1 and P2 is use them to approximate the derivatives at the beginning and the end at P0 and P3. Well, how do we approximate a derivative? We do it like we did in Calculus 1. We take the difference of the y values over the difference of the x values. Well, if we do what we did before, that say these data points are equally spaced, so this is at u equals 0, u equals a third, 2/3, and 1, then the derivative is p1 minus p0 approximately divided by 1/3, and likewise at the right end it's approximately p3 minus p2 at a third. So I simply take those values and put them into the same equations that we started with for the Hermite form, namely so we have the same endpoint conditions that we at u equals 0 we have to interpolate c0, so we evaluate the cubic at 0 we get p0 equals c0, and again at 1 we get p3 is c0 plus c1 plus c2 plus c3. But now when we take the derivative, instead of using, and we take the derivative at 0, well that gives us, this is c1 here, I just noticed this. This should be C1, not C0, which we get from taking the derivative of P of u and evaluating u equals 0. And instead of saying it's a value P prime of 0, it's this approximate value P1 minus P0 over a third, which puts the 3 up on top. And likewise, at u equals 1, the derivative was C1u plus C2u squared plus 3C3u cubed. That gives me C1 plus 2C2 plus 3C3 again. And now on the right, on the left, that's equal to the approximate derivative P3 minus P2 over a third. So here's 4 equations and 4 unknowns. They're a little bit more complex than what we had before, but what I can do is substitute P0 into this equation, get an equation for P1, substitute for P3 in this equation to get an equation for just P2. Then I have 4 equations and the 4 unknowns, and I can solve those and get, once I solve them, I get that the constants C1 through C4, C0 through C4, are given by the Bezier matrix times P, which looks like like this. Again, it's got smaller values in it than the interpolating matrix, which is good. It comes out nice integer values too. And if we do exactly what we did before and rearrange things so that if we look at U transpose M, those give me the 4 blending polynomials, and then each one multiplying one of the data points, P0 plus P1, so on. And if you look at them, this is what you get. This one, notice that each one, see, since you interpolate P0 and P3, the last 3 have to have a U term in it to force them to 0 at U equals 0, and the first 3 have to have a 1 minus U in them to force them to be 0 over here. It turns out they have this very nice form over here, and notice that they're always positive. They have 2 properties that are very important to us that we're going to use. One is that they're always positive, non-negative, and second, that their maximum value is 1. And in fact, the P2 and B2 and B3 have values much less than 1, but the important point is that the values are less than 1. And in fact, if you sum these all up, that's probably the third crucial point, these sum to 1, which is very, very going to be very, very helpful. You have to multiply them out to see. So that all the zeros are either at 0 or outside of the 0, 1 range. So there aren't these rapidly changing values of any of the blending polynomials. They're all fairly smooth. Again, B0 and B1 are reflected to give you B3 and B2 and B3. And so if you look at these polynomials, in fact, they're the cubic equivalent, the cubic version of what are called the Bernstein polynomials. And let me just mention that. They look like this, and they all have these nice properties. All the zeros are either at 0 or 1. In fact, I should have really emphasized that here. No, the zeros can't be outside this range. Here, all 3 zeros are at 1. Here, one of the zeros is at 0, and 2 are at 1, and flip that over for the second and third. So all the zeros are at 0 and 1. And in fact, for this general form, they have that property that all the zeros are at 0 and 1, which you see from on the right here, and they all sum to 1, and they all have values between 0 and 1 inside that interval from 0 to 1. So they all have this nice property, which says that, essentially what it says is that if you go to a higher degree Bezier form, from cubic to, generally you go up in powers of 2, from cubic to 5th power to 7th power, you get all of the good properties that you had with the cubic. And so if you sum up these 3 things at the end, or that all the zeros are at 0 and 1, and that it adds up to 1, and they're all between 0 and 1, that sounds a lot like what we were talking about when we talked about the convex sums earlier in the class when we first started talking about geometry. And that gives us what's called, putting all kinds of things together that we've already talked about, gives us what's called the convex hull property, that says that the curve has to lie within this little trapezoid formed by the 4 data points, which is just a remarkable result, but it really comes from the fact that these Bernstein polynomials have this wonderful sort of affine sum convex hull kind of property. So that says that, look, that if it has to be inside the convex hull, then I know, even though it only interpolates P0 and P3, it has to be close to P1 and P2. It can't get outside of this box over here, and that's a very valuable thing to have about curves. Even though things like the Hermite form are very nice, you don't have this wonderful property that says, look, I can tell you how bad the error can possibly be. And also, as we'll see in the next lecture when we start talking about how we render these curves, you can say, wait a minute, if it's going to be close to this, here's a real simple way of rendering this curve approximately. Why don't you just draw these 3 line segments from P0 to P1 to P1 from P1 to P2 and the third to P2 P3. Very reasonable thing to do if you have a fair amount of data points. Don't worry about that this is a cubic polynomial or perhaps a higher order polynomial with more data points, you can just render the convex hull. So we'll talk about that more in the next lecture. Now you can also do the same thing that we did with the interpolating curve, is go to the Bezier patch by saying, well, if I do this with two parameters and I argue that for one of the parameters being held constant, that all the resulting curves in the other parameter have to be Bezier curves themselves, you get exactly the same form. This is called a separable form or a tensor product form. Wow, you're friends with the terminology. So it's if you express everything in terms of data points, you have these little blending patches that you sum together, 16 of them, and each one is the product of a blending curve in U times a blending curve in V, and times the 4x4 data array here in the center. So now notice that the patch has the same sort of properties we had with the curve. You interpolate now the four corners of the patch. You don't necessarily go through any of the other points, the other 12 points, but you can talk about the convex hull of those 16 points, just as we talked about convex hulls earlier, that you can start connecting all the pairs of points with line segments, and that determines some polygonal shape in 3 dimensions, and the curve has to lie inside, so you know that it comes close to these points, even though none of these points need lie on the curve except on the surface, except at the 4 corners. So this is a much better way of doing things. You don't exactly get continuity at the corners. So you say, wait a minute, these are not really Hermite curves, they're close to Hermite curves. So what happens to the patch over here and the patch over on the left, the right, the right up here and down here? And the answer is, well, you're only going to really interpolate the corners exactly. So these patches don't really have first derivative continuity in U and V, but they're fairly close, and we'll see with splines we can get a little better than that, actually much better than that. So you're coming close, but you're much better off than you were with the other forms. So you really don't have quite the derivative continuity that you'd like. So what do? Well, one strategy is to go to higher order curves, use the Bernstein polynomials. You still don't get quite derivative continuity, but you have much better approximations than you had before, but you're doing more work when you do the evaluation to try and render things. Now, to mention the old fixed function OpenGL, that actually supported these Bezier curves and surfaces through functions that were called evaluators, which basically were just functions that evaluated the Bernstein polynomials for any degree. They're not there, but it's easy enough, as we'll see in the next lecture, to build in the equivalent yourselves and do the rendering yourselves. The other question is, what about applying the conditions? Because I didn't really tell you what exactly are the conditions over here for this interior point, how do they relate back to here? And they relate in funny ways to what's going on here at the corners. If you look at let's look at P11 minus P00. Sometimes it's called a twist, because this little polygon here, well, let's look at these 4 points. They form a quadrilateral, which is not necessarily flat. So you can look at things like P11 minus P00 and say if it doesn't lie in this plane, it's giving you a measure of how this little quadrilateral is twisted from being flat, and that can get used in CAD applications. But we're going to leave that here and not worry about the physical interpretation of what these points might mean. So rather than go to higher order and look at different conditions, because if we look at different conditions, we may no longer have that wonderful convex hull property, and say, well, can we do better? And you'd think that let's go think back in the curves, with a cubic curve and 4 points, haven't we done all we could possibly do? There are only 4 parameters we can control. In fact, we can do better, and we'll see the price we have to pay for doing that, but we can actually get more continuity at the join points with a cubic than we could with the Bezier. In fact, we'll get second derivative continuity at those join points. So let's look at what are called B-splines, and the B stands for basis splines. It's because they form a basis for the curves. So we're going to use them in general, and the thing we're going to do here is, suppose I have 4 points, and we're going along. See, when we talked about the Bezier form, we say, okay, we use the first 4 points, P0, P1, P2, P3, to determine the first little segment that goes between P0 and P3. Then we use P3, P4, P5, P6, so that we repeat the point just as we did with the interpolating polynomial. Now let's look at things a little bit differently here. Suppose the first one might go from P0, P1, P2, P3, but let's use that to only define a curve between P1 and P2. Okay, so P0 and P3 are going to be used to evaluate the curve, but we're not going to use the part except between P1 and P2. And likewise, when we move on, the next one will use P1, P2, P3, P4, but only get the curve between P2 and P3. That's what's going to give us. So each segment that we get is going to be shorter. It's going to be a third the length of the segments we were getting before, but we're going to be able to apply more conditions to get second degree continuity at these join points. So because you're only getting a third of the distance on each of the things, you're doing 3 times as much work for the curve, because you're only adding, one way to see it is every time you evaluate a new one, you're only adding on 1 point. Before, when we did interpolating in Bezier, we're adding on 3 points each time. Now we're only adding on 1, so you're doing 3 times as much work. And the problem is, if you go to surfaces, which is what we generally in the real world spend more time on than curves, then you're doing the square of that, or 9 times as much work, but you get a much, much better approximation. So here's kind of how the argument goes briefly. If you do go through exactly the same thing and say you get only this part and you enforce second degree continuity at these join points. So you got to match this curve to the one on the left, and you have to match what goes on in P1 to the one on the right. This is all in the book. You get a matrix that you use, which looks, here it is. This is called the cubic B-spline matrix. And you use it exactly the same way. You use it with data points P0, P1, P2, P3. The numbering here traditionally is a little bit different, but not really crucial to what we're talking about here. Use these 4 points, and you get the curve, and you simply only evaluate it between these two, between P2 and P3. Okay, so what do the resulting blending functions look like? We go through exactly the same analysis, compute the blending functions over here, the 4 blending functions, by doing this matrix multiplication. And here they are. The 2 at the ends are pretty easy. You have a triple root at 1 and a triple root at 0, and then you have these values in here. It turns out, again, these curves, here's a little picture of them that I plotted out. They're maximum at 1, so they're between 0 and 1, all inside of this region. And if you sum up these blending functions again, they all sum to 1. So that says, well, gee, that looks like the convex hull property again. And in fact, they are. See, they sum to 1 for any value of u. So that's why the convex hull property holds at any value of u. So therefore, again, the curve, even though you're using it only between P2 and P3 here, you still are always inside that convex hull, and you're not necessarily, in general, you're not interpolating any of the points. You're getting a little curve segment that's in this convex hull. That's good. And when you connect it to the next curve on the left and the next curve on the right, you'll be inside the convex hull of the 4 data points on the one on the left and the convex hull of the 4 data points on the right, and you have continuity at the join point, you have first derivative continuity at the join point, and second degree continuity at the join point, which if you're trying to design surfaces is generally enough, because there are a couple of arguments for that. One of which, let's go to the surface, I'll come back to that in a second. That if you do this, again, go to surfaces from curves, you once more get 16 blending functions, which are the product of the 2 blending functions. Mathematically, it looks exactly as what we had before, except that you have the spline matrix and its transpose in here instead of the others. But now, for those 16 data points, you're only getting the patch defined over, as we said, 1/9 of the area. So this is, now why is second derivative continuity all we need? Basically, these splines come back as a name that people used for devices they used first in shipbuilding to get the surface of the ship. They would put pegs in, and they would bend metal to be held in by those pegs that determine the shape of the hull. Those were called spline curves. Now, if you ever did any kind of drawing or architectural drawing, we used to have to buy these plastic spline curves that we could trace with a pencil, but they were used in a very similar kind of manner. So there's a long history, and some of the reason that the second derivative is so crucial in that is that when metal bends, it's as long as that second derivative is continuous, you're not going to notice the difference. It's both a visual thing and a property of the metal. That if I take 2 pieces of metal and I can ensure that the second derivative is the same at the join point, you're really not going to see the difference, and that's sufficient for doing design of shapes that you're actually going to produce. Now, the other way of looking at this, just briefly, is that if you look at a spline from the point of view of one of the data points, each data point now is going to contribute to 4 different little splines, and each little spline is only used over 1 segment. So we can write things down. If I write the entire spline for all of the data points, then I have functions bi of u times each of the data points. So rather than looking at it all 4, I put everything together into a single function, but this function bi of u is 0 except for the 4 points that it's going to use, or the 4 segments where that data point pi is going to be used. It's going to be 0 every place else. This gives you this wonderful locality property, which is crucial to what we're doing, and this really contributes to the stability of all of these segment things. If I change something of one of the data points, it's not affecting anything other than this one little region of the 4 little segments it controls. If I do the same thing with interpolating or Bezier form, I change one of the points, depending on whether it's the end point or interior point, it only affects 1 segment, or at worst 2 segments. So you have a very local property that if you change something in one region, it isn't going to affect something all the way on the other end, which is not true if you use these sort of global high-order curves. So these basis splines are very interesting mathematically, but this locality property of only being non-zero over 4 segments is crucial to the smoothness and their usefulness. So if I look at one of them, you can look at what they are over each region in terms of the blending polynomials. But if you draw it out, it looks like this, that you use B0 to get this little part, you use B1 to get this part, and then B2 and B3 to get the other 2 parts. And this is the part that multiplies one particular data point. The next one gets multiplied by a shifted version of this, and then the next one gets multiplied by a shifted version of that. Now, the one thing I left out that I probably should have mentioned is back here. Let me come back here for a second. That what do you do if this is P0 and this only starts off over here, u equals a third into it? What happens at the left
and the right at the left end of the whole thing and at the right end of the whole thing. And generally we have to apply some other condition there to pin down the two ends. And I talk a little bit about that in the book, but we're not going to necessarily, we don't really at this point need to go into that kind of detail. So here's the function. And if I just try and generalize that slightly, that what we can do is we can do this at any degree, and the spacing doesn't have to be uniform. You have data at points called the knots, which are not necessarily the join points. You can repeat the knots. You can repeat data multiple times, and that will force you to interpolate certain points, in particular at the two ends. And there's something called the Cox-de Boer recursion, which gives you a way of evaluating this for fairly efficiently and for any order spline. Don't need to worry about this here. I'm going to give you some very interesting methods for evaluating in the next lecture. But finally, I want to mention NURBS, because NURBS have some very interesting property, and again, here's one you can impress your friends with. It stands for non-uniform rational B-spline curves and surfaces. So what happens there is that instead of doing it in 3D space, we're going to go into 4D space. So it's very much tied to what we do in homogeneous coordinates, but the interpretation here is that the W is used to give some additional importance or less importance to particular data points. So each data point is being multiplied by W. So if you have a data point, the ith data point, xi, yi, zi, you can associate a constant with it, wi, that multiplies each one. So you have used wi, xi, wi, yi, and wi, zi. Well, if you look at that, you can say that sure looks like what we were doing with homogeneous coordinates, and the way that we get back to x, y, and z is to divide by w. And in fact, yeah, that's what we're going to do. But if we look at the w, so each xi, yi, zi will have a different wi potentially, then the wi's can be looked at as the control data for a polynomial p of u, which gives me the w value. So what do you do at the end? You get three polynomials, x of u, y of u, and z of u, a fourth polynomial, w of u. But to get back into normal space, we do essentially a perspective division. So I use x of u over wu, y of u over wu, and z of u over wu. That's what's called a rational function. The ratio of two polynomials in u is a rational function in u. The spacing doesn't have to be uniform, so you don't have equally spaced u's necessarily. So that's where you get the non-uniform in the name. And each one is still a B-spline. So that's how you get NURBS. So it's a NURBS surface or a NURBS curve. And they were supported in an extra library that went along with the old OpenGL. Now, the other thing that's important is that if you're really going to want things to be exactly correct when you start viewing them, that splines and generally B-splines and Béziers aren't quite right if you start doing perspective viewing. It turns out because of this W that you're using over here and you're doing a perspective division, NURBS turn out to be correct when you do perspective viewing, which does, if you're going to really want, really accurate models or really accurate animations with curved surfaces, that can be important. Then there's another thing that you can do and show that quadrics are a special case of NURBS. Now you'll perhaps appreciate that a little more in the next lecture, but let's look at it this way, that if you go back to the first lecture we talked about curves and surfaces, we said quadrics could be represented as implicit functions, but we could evaluate them because they reduce to a quadratic curve. When you put a line through them, you can always find those points of intersection. But you don't want to have generally two different ways of dealing things in your own graphics library. You don't want to deal necessarily with quadrics in one way and parametric polynomial surfaces and curves in a second way. Well, it turns out that quadrics, if you pick the parameters carefully, are a special case of NURBS. So NURBS include all of the types of curves we've talked about so far, plus they include the quadrics if you adjust things correctly. So we'll talk about that a little bit more. No, we're not going to talk about it a little more. I don't want to do that. It's getting into too much detail. But we will talk about evaluating quadrics and evaluating Bezier and spline curves in a little bit. And finally, there's one more thing we'll do next time that I think you'll find interesting. And this is one of the reasons I really did want to introduce at least Bezier curves in this class, is that we'll show that if you know how to do Beziers, you know how to do any other form, because you can always convert easily any other curve to a Bezier equivalent Bezier curve. And I'm going to give you some really neat ways of evaluating Bezier curves and surfaces in the next lecture.